In 1985, Carl Sagan called a physicist and asked a question that was supposed to be about a novel. What came out of that phone call was 40 years of research that nobody planned and nobody has fully explained yet. The answer to Sagan's question turned out to be yes. A human being could theoretically travel through a tunnel in space-time, but the price tag was staggering. Negative energy equal to the mass of the entire Earth, compressed into a shell 1 centimetre thick. That was just the beginning. Because in the decades that followed, physicists kept building new versions of that tunnel using completely different mathematics, different frameworks, different assumptions, 6 independent models, and every single one of them, without anyone adding a rule by hand, refused the same thing: backward time travel. The math just keeps saying no, not the same no, a different no each time. Which raises a question that is sitting right at the edge of everything we think we understand about reality. Is causality a law the universe enforces, or is the universe itself built out of causality? The way a house is not just inside its walls but made of them? Get comfortable. Subscribe if you have not, and stick around, because the pattern we are about to follow goes somewhere that most physics explainers never quite reach. Let's get into it. Part 1. The rule nobody wrote. There is a door hidden inside Einstein's equations. It has been there since 1915, sitting quietly in the mathematics like a trapdoor in the floor of a house that everyone agrees is structurally sound. The door is real. The equations allow it. Physicists have studied it for over a century, mapped its dimensions, argued about what it would cost to open it, and built entire theoretical frameworks around what you might find on the other side. And in all that time, across all those frameworks, across every independent approach physicists have taken from completely different directions using completely different tools, one thing has never happened. Nobody has ever managed to walk through. Not because the door disappears, not because anyone erases it from the math. The door stays. It just never quite opens in the way that would matter most. And the specific thing it refuses to allow every single time without exception is this: you cannot use it to travel backward in time. Think about how strange that is for a moment. We're not talking about an engineering limitation. We're not talking about the difficulty of gathering enough fuel, or the practical impossibility of surviving the journey, or the sheer cost of building something at the scale required. Those would be ordinary obstacles, the kind physics hands us constantly. What we're talking about is something stranger and more fundamental. The mathematics itself, when pushed in the direction of backward causation, does something unexpected. It refuses. Not violently, not with a single rule someone programmed in, but softly, inevitably, in a different way each time. The mechanism changes, the outcome does not. This has happened so many times now, across so many different models developed by independent researchers who are not coordinating their results, that it has stopped looking like coincidence. It has started looking like a pattern. And patterns in physics are not decoration. Patterns are how we find the deepest laws. Let us start with why wormholes matter at all, because there is a tendency to treat them as science fiction furniture. The kind of thing that gets dropped into a movie when the plot needs to move someone from one side of the galaxy to the other without the inconvenience of taking a few million years to get there. But wormholes are not science fiction. They are solutions to Einstein's field equations, which are the most rigorously tested description of gravity and space-time that humans have ever produced. When we say wormholes are allowed by those equations, we mean they are allowed in the same sense that black holes are allowed, which is to say they are allowed in the sense that they almost certainly exist somewhere in the universe, whether we have confirmed it observationally or not. What a wormhole is, at its most fundamental, is a connection between two separate regions of space-time. Not a tunnel through space, in the way you might imagine a tunnel through a mountain, where you are moving through the rock that fills the middle. The wormhole is more subtle than that. It is a topological feature of space-time itself, a fold, a junction, a place where two distant regions share a boundary that would not exist if the space-time were flat and ordinary. You can think of it this way. Take a sheet of paper and mark 2 points far apart on it. The ordinary distance between those points, measured across the flat surface, is large. Now fold the paper so that the 2 points nearly touch, and poke a hole connecting them. The distance you travel through the hole is tiny. The distance across the unfolded paper has not changed. Both distances are real. The wormhole is the hole you just poked. This matters because of what it does to time, and this is the part that most people miss, the part that makes wormholes genuinely dangerous, as concepts rather than merely exotic. Space and time are not separate things in Einstein's universe. They are a single fabric, spacetime, and anything that shortcuts through space necessarily also affects time. If you take a shortcut through space that is significant enough, you do not just arrive at your destination faster in the ordinary sense. You arrive there with a different relationship to the time that passed for everyone who did not take the shortcut. And if the shortcut is extreme enough, and if it connects 2 points that are moving relative to each other in the right way, the difference in elapsed time becomes large enough that you can arrive at your destination before you left your origin. Not metaphorically, literally. This is the trap that is hidden inside every wormhole solution. It is not something you choose to add. It comes with the geometry. Any traversable wormhole, one that allows matter and information to pass through it, is potentially a time machine. The two things are not separate features. They are the same feature. Which means that if wormholes are real and traversable, and if physics has nothing to say about how they behave, then causality itself, the simple principle that causes precede effects, that you cannot get a reply to a message before you send it, that your grandfather cannot be killed before your parent is born, is not safe. And here is what makes this the most interesting open question in modern physics. Every time researchers have developed a new wormhole model and pushed it toward the regime where backward time travel would become possible, something in the math has intervened. Not the same something, not a single rule that kicks in and says forbidden. A different mechanism each time, operating through a different part of physics, achieving the same result. Quantum fields do it one way, geometry does it another. The constraints of entanglement do it a third way, the energy requirements do it a fourth, the models are independent, the outcome is identical. This is what we mean by convergence, and convergence in physics is never accidental. The question that convergence raises is one that physicists are genuinely, seriously debating right now, and it is a question that reaches far outside physics into something more fundamental about the nature of reality. Is causality a rule that the universe enforces, a law written into the code like a speed limit with consequences for violations? Or is causality something deeper than that? Is it the structure the universe is made of? Is it the skeleton inside the body of everything? The thing that, if you removed it, would not just break a law but dissolve the universe itself? We're going to follow that question through 4 decades of physics research. We're going to meet the people who stumbled into it, the experiments that tested it, the mathematical structures that seem to know the answer even when the physicists studying them do not. And we're going to end up in a place that is genuinely strange, not in the comfortable way that science sometimes offers when it tidies things up, but in the uncomfortable way that science offers when it discovers that the question it was asking was pointing at something much bigger than the question itself. The door exists. It has always existed. The mystery is not whether it is there. The mystery is what it means that it will never open. Part 2, the phone call that started it all. In the summer of 1985, Carl Sagan was writing a novel. He had spent years accumulating the reputation of perhaps the most effective science communicator of the 20th century. The man who had made the cosmos feel personal and immediate and staggeringly large all at once, who had a gift for finding the human scale inside the astronomical scale without shrinking either one. Now he was writing Contact, and he had a problem. The novel needed its protagonist to travel from Earth to the star Vega and back. Sagan wanted this to feel real. He was not interested in hand-waving the mechanism in the way that most science fiction simply declares that faster-than-light travel exists and moves on. He wanted a mechanism that was at least plausible, that would not make the physicists in his audience wince, that had some grounding in actual physics even if it required extraordinary assumptions. He had been using black holes as his proposed method, the idea that you could fall through one and emerge somewhere else, and he sent his manuscript to Kip Thorne, the Caltech physicist who was one of the world's leading experts on general relativity, and asked him to check it. Thorne read the manuscript and called Sagan back. The black hole solution would not work, he explained. Not because it was too exotic, but because the geometry was wrong. Falling into a black hole does not take you somewhere else. It takes you to a singularity. The mathematics does not produce an exit. If Sagan wanted a physically plausible interstellar shortcut, he would need something different. What happened next is one of the more interesting pivots in the history of science. Thorne could have simply corrected the error and moved on. Instead, he found himself genuinely curious about the underlying question. Sagan had asked, in effect, whether Einstein's equations permitted any solution in which a human being could travel between widely separated points in spacetime in a time that was reasonable by human standards. Not whether it was practical, not whether it was currently possible, whether the equations allowed it in principle. Thorne assigned the problem to his graduate student Michael Morris, and together they approached it in a way that was unusual and elegant. Instead of starting with a known solution and asking whether it was traversable, they started with the requirements for traversability and asked what geometry would satisfy them. They essentially worked backward. They said, here is a human being who needs to survive the journey. What properties must the wormhole have? What must the curvature be at the throat? What must the tidal forces be? What must the geometry look like at the entrance and exit? And then they solved for that geometry. The solution they found, published in 1988 in the American Journal of Physics, became known as the Morris-Thorne wormhole. It was the first traversable wormhole solution in the history of physics, and it came with a price tag that was genuinely staggering. To hold the throat of the wormhole open, to prevent it from pinching off before anything could pass through, the geometry required what physicists call a violation of the weak energy condition. The weak energy condition is, in ordinary language, the requirement that energy density cannot be negative. In classical physics, this seems almost trivially obvious. You cannot have less than nothing. Energy density is always zero or positive. But in quantum mechanics, this is not quite true. There exist configurations of quantum fields where the local energy density is negative, where a region of space has, in some meaningful sense, less energy than the vacuum. This sounds paradoxical, but it is not. The vacuum in quantum mechanics is not empty. It is a seething background of fluctuations, of particle-antiparticle pairs constantly appearing and annihilating, of quantum fields vibrating at their lowest possible state. This vacuum has an energy of its own. Negative energy density means a local region where the energy is below even this vacuum baseline. It is less than nothing measured against the least possible something. The Morris-Thorne calculation showed that you would need this negative energy, this below vacuum energy density, arranged in a shell roughly 1 centimeter thick around the throat of the wormhole. And the amount you would need was not small. The total energy involved was comparable to the rest mass energy of the entire Earth, which is a number you can calculate directly from Einstein's most famous equation, E = mc squared, and it comes out to approximately 5 times 10 to the 41 joules. Spelled out, that is 5 followed by 41 zeros, the total energy output of our Sun over roughly 20 million years, compressed into a shell 1 centimeter thick, in negative form. Thorne did not consider this a refutation. He considered it a constraint. The universe was saying, yes, this is geometrically possible, and here is the price. The price was extraordinary, perhaps impossibly so from any practical standpoint, but it was a price, not a prohibition. The universe was not saying no. It was saying maybe, but here is what it will cost you. The Casimir effect, discovered experimentally long before Morris and Thorne did their work, provides a small but real proof that negative energy exists. If you take 2 uncharged metal plates and place them extremely close together in a vacuum, the vacuum energy between them is slightly lower than the vacuum energy outside them, because some of the quantum fluctuations that would normally exist between the plates are excluded by the boundary conditions the plates impose. The result is a tiny attractive force between the plates, measurable, reproducible, and genuinely caused by a region where energy density falls below vacuum. The Casimir effect produces negative energy densities of roughly 10 to the -3 joules per cubic meter when the plates are about 1 nanometer apart. You would need something like 10 to the 44th joules per cubic meter to stabilize a wormhole with a 1 meter throat. The gap between what the Casimir effect produces and what wormhole stabilization requires is roughly 47 orders of magnitude, which is not an engineering gap but an unfathomable chasm, and yet the point stands. Negative energy is real. The universe allows it. The Morris-Thorne wormhole is, in the most precise possible language, conditionally permitted. And that condition, the energy requirement, is the first of many times we will watch the universe set a price so high that the desired destination becomes unreachable, without ever being explicitly forbidden. The door is there. The universe just keeps asking for more than you have. But here is what you should carry with you as we go forward. The energy requirement stops you from building a wormhole. It does not, on its own, stop a wormhole that already exists from becoming a time machine. And that problem, the time machine problem, is sitting quietly in the geometry, waiting to be discovered. We have not found the trap yet. We have only found the entrance fee. Part 3. The first trap, hidden in the geometry. Before we can understand why every wormhole becomes a time machine, we need to correct a mental image that almost everyone carries around without knowing it is wrong. When most people hear the word wormhole, they picture a tunnel, a cylindrical corridor with walls stretching through some kind of intermediate space, connecting two mouths the way a subway tunnel connects two stations. Matter enters one mouth, travels down the corridor and emerges from the other mouth. The tunnel is the wormhole. The inside of the tunnel is the wormhole. This picture is vivid and intuitive and almost completely incorrect. A wormhole does not have an inside the way a tunnel has an inside. It does not pass through some intermediate space because there is no intermediate space in this picture. Space-time is not embedded in anything larger. There is no outer container that space-time sits inside of, no higher dimensional room that the wormhole punches through to get from one side to the other. What a wormhole actually is, mathematically, is a modification to the topology of space-time itself. Here is a better picture. Topology is the branch of mathematics that studies properties of shapes that do not change under smooth deformation. A coffee cup and a donut have the same topology, because one can be smoothly deformed into the other without tearing. A sphere and a donut do not have the same topology because getting from one to the other requires tearing a hole. Topology is about global connectivity, not about local shape. And a wormhole is a topological feature of space-time, a place where the global connectivity of space-time is different from what flat ordinary space-time would have. Take your sheet of paper again, the one we used earlier. Flat ordinary space-time is like a completely flat infinite sheet. Every point is connected to nearby points in the straightforward way you would expect. Now mark two circles on that sheet, far apart. Identifying the two circles with each other, declaring that they are the same boundary, produces a wormhole topology. The two distant regions now share a boundary. Nothing had to pass through anything. There is no corridor. The two mouths of the wormhole are simply declared to be the same surface, and the space-time geometry accommodates this declaration. The throat of the wormhole is not a passage through space, it is the shared boundary itself. What this means practically is that the throat is extremely thin in the mathematical sense. There is no volume inside the wormhole that you travel through. You enter at one mouth and the geometry immediately delivers you to the other mouth. The journey time through the wormhole can be extremely short, essentially instantaneous in the limit. This is what makes it useful as a shortcut, and this is also what makes it dangerous. The historical precursor to traversable wormholes is the Einstein-Rosen bridge, which Albert Einstein and Nathan Rosen described in 1935 while trying to understand the Schwarzschild solution to Einstein's equations, which is the simplest description of a non-rotating black hole. They noticed that the geometry of the Schwarzschild solution, when extended to its full mathematical completion, does not just describe the exterior of a black hole, it describes a connected geometry in which two separate regions of space-time, two separate universes in the most radical interpretation, are joined at a central surface. This central surface is the Einstein-Rosen bridge. It sounds like a wormhole. It is in fact a wormhole, but it is not a traversable one. The reason is a subtlety about the geometry that requires some care to explain. In spacetime physics, paths through spacetime come in three types. Time-like paths are paths that a massive object can travel. They have a well-defined sense of past and future, and the traveller on such a path always experiences time passing. Null paths are paths that light travels, moving at the speed of light with zero proper time elapsed. Space-like paths are paths that connect two events that are, in the language of relativity, outside each other's causal influence. No signal, no matter how fast, can travel between two events connected only by a space-like path, because getting from one to the other would require going faster than light. The Einstein-Rosen bridge is space-like. The path through it is not time-like or null, it is space-like, which means no particle and no signal can actually traverse it. Any attempt to enter the Einstein-Rosen bridge leads not to the other side but to the singularity at the centre of the black hole, where the curvature of spacetime becomes infinite, and the laws of physics as we know them break down. The bridge is geometrically present but physically impassable. It exists for only an instant before collapsing back, and that instant is not accessible to any traveller moving at subluminal speeds. Penrose diagrams, developed by Roger Penrose in the 1960s, are a way of drawing the entire causal structure of a spacetime on a finite page. In a Penrose diagram, every point represents a sphere of spacetime, and the angles of lines drawn on the diagram encode whether paths are time-like, null, or space-like. Light always travels at exactly 45 degrees. Anything slower moves on a steeper line. Anything faster, hypothetically, would move on a shallower line. The Penrose diagram for the fully extended Schwarzschild solution shows the Einstein-Rosen bridge very clearly, and it shows with equal clarity that no time-like or null path crosses from one side to the other. The bridge is there. It is just not accessible by anything real. The Morris-Thorne wormhole was designed to avoid this problem by carefully choosing the geometry, by specifying the exotic matter configuration that holds the throat open. Morris and Thorne created a solution where the path through the wormhole is time-like. A traveller who enters one mouth and emerges from the other has followed a physically realizable trajectory. They have not violated any local law of physics at any point along their path. This is why the solution was interesting and why it required exotic matter to sustain. Making the path time-like requires counteracting the natural tendency of the wormhole geometry to close, and that counteraction requires negative energy. But here is the trap, and it was Morris and Thorne themselves who noticed it first. When you examine the Morris-Thorne wormhole solution carefully, you find that the two mouths of the wormhole are not at the same point in time. The geometry that connects them also connects different time slices. There is an inherent time offset built into the structure. This seems minor at first. Who cares if one mouth is a few seconds ahead of the other? But it is not minor, because that time offset can be manipulated. It can be made large, and once it is large enough, a traveller can enter one mouth of the wormhole, emerge from the other mouth in the past, travel the ordinary way back to the first mouth, and enter it again, thereby creating a closed loop in time, an event that is its own cause, a journey that has no beginning. The trap was in the geometry from the start. Making the wormhole traversable did not remove the trap, it opened it. Part 4, How Every Wormhole Becomes a Time Machine. The year is 1988, and Morris and Thorne have just published their traversable wormhole solution. Within the same year, they and Ulvi Yurtsever publish a follow-up paper that is, if anything, more unsettling than the original. In this paper, they show explicitly that any traversable wormhole can be converted into a time machine. The mechanism they describe is elegant and unavoidable, and it relies on a piece of physics that Einstein established in 1905 with the special theory of relativity. Relativity tells us that time passes at different rates for observers, moving relative to each other. This is not a metaphor or an approximation. It is a measured, confirmed physical fact. A clock moving at high speed relative to a stationary clock will tick more slowly, and when the two clocks are brought back together, the moving clock will show less elapsed time. The faster you move, the more extreme the effect. At very high fractions of the speed of light, you can accumulate massive time differences over what feels to you like a modest journey. Now imagine that you have a traversable wormhole with two mouths. Call them mouth A and mouth B, both sitting stationary in space connected by the wormhole throat. In the initial configuration, the two mouths are synchronized. Whatever time it is at mouth A, it is the same time at mouth B. This seems natural and obvious. Now you take mouth B and accelerate it to near the speed of light. You move it away from mouth A at, say, 99% of the speed of light. Let it travel for what feels to you, the external observer, like several years, and then bring it back. Due to relativistic time dilation, mouth B has aged much less than mouth A during this journey. Mouth B is now in the past relative to mouth A. The gap might be hours or days or years depending on how fast you moved it and for how long. And here is the critical point. The interior of the wormhole does not care about this. The throat connects the two mouths regardless of how much their external time coordinates have drifted. So now you have a system where mouth A is in the present, mouth B is in the past, and they are still connected by a throat you can walk through. If you enter mouth A and walk through the wormhole throat, You emerge from mouth B into the past. You can then walk through ordinary space back to mouth A's location, wait for the moment in the past when you originally departed, and watch yourself leave. You have created a closed time-like curve, a loop in time that has no beginning and no end. Your entire journey is its own cause and its own effect simultaneously. This is not a hypothetical scenario that might fail for some technical reason. It follows directly from the mathematics. The only inputs are special relativity and the existence of the traversable wormhole. No additional assumptions are required. Any wormhole you can walk through, given enough time and the ability to move one of its mouths, becomes a time machine. This is not a problem with Morris-Thorne specifically. It is a problem with traversability itself. Traversability implies time machine availability. The two are the same feature. The closed time-like curve is the mathematical object that encodes backward time travel. It is a path through space-time that loops back on itself, a world line that returns to its own past. Any space-time that contains a closed time-like curve contains a region where causality, the principle that causes precede effects, is violated. Not locally violated in some limited way that only affects a few events. Globally violated in the sense that the entire causal structure of space-time in the region of the loop becomes logically inconsistent. The grandfather paradox is the classic illustration. If you travel back in time and prevent your grandfather from having children, you yourself were never born. But if you were never born, you never travelled back in time. But if you never travelled back in time, you never prevented your grandfather from having children. So your grandfather did have children. So you were born. So you did travel back in time. So you did prevent your grandfather from having children. The scenario generates a logical contradiction that cannot be resolved by any consistent assignment of truth values to the events involved. The bootstrap paradox is slightly different and in some ways more disturbing. You travel back in time and give a young physicist the equations for, let us say, a traversable wormhole. The young physicist uses them to develop traversable wormhole technology. Years later, the same physicist, now old, travels back in time and gives the equations to their younger self. Where did the equations come from? Nobody derived them. They exist only because someone received them from the future, which they can only do because someone travelled to the past, which requires the wormhole technology described by the equations. The information has no origin. It is its own cause, which means the universe contains a piece of information that required no energy or intelligence to create. It appeared from nothing through the structure of the time loop. These are not mere logical puzzles. They are descriptions of space-time configurations that, if they existed, would mean the universe contains physical processes with no causal origin, which violates conservation laws, information principles, and the basic coherence of physics as a descriptive enterprise. If closed time-like curves are possible, then the entire framework of physics, the idea that the universe has a consistent state at each moment that determines the state at the next moment, collapses. And yet here is the situation in 1988. Morris and Thorne have just proved that any traversable wormhole becomes a time machine. The exotic matter requirement might prevent any such wormhole from existing in practice, but it is not clear that the physics itself prohibits it. There is no theorem, no proof, no mechanism that enforces a prohibition. There is just an energy price that seems very high. Is the price high enough? Does it guarantee prohibition? Or does it just guarantee that we cannot build one, while leaving open the possibility that one already exists somewhere, already converting itself into a time machine, already generating closed time-like curves? That question is what the universe is going to answer, just not in the way anyone expected. Part 5, Hawking's unfinished warning. Stephen Hawking spent the last decades of his life worried about time machines. Not in the anxious, hand-wringing way, but in the rigorous, let us work out what the math actually says way that was characteristic of his approach to every problem he found genuinely important. And he found this one genuinely important because it sat at the intersection of quantum mechanics and general relativity, which was exactly the territory where he had done his most original and lasting work. In 1992, Hawking published what he called the chronology protection conjecture. The conjecture was simple to state. The laws of physics, he proposed, prevent the formation of closed time-like curves. Whatever mechanism is required, whatever piece of physics ultimately enforces the prohibition, the universe does not allow backward time travel. Causality is protected. What made this a conjecture rather than a theorem was that Hawking could not prove it. He had strong reasons to believe it was true. He had intuitions formed from decades of working with the deepest structures of general relativity and quantum field theory. He had the suggestive evidence that in every case he knew of where closed time-like curves seemed to be forming, something went wrong. But he could not point to a single unifying principle that guaranteed the protection. He could not identify the mechanism. He was naming a pattern he had observed and betting that the pattern was real. This is actually a significant thing to do in physics. Naming a pattern you cannot yet explain is a way of marking territory, of saying this is where a deep truth is hiding, even if we cannot yet see its face. The chronology protection conjecture said, in effect, we do not know why the universe protects causality, but we should start looking seriously for the answer, because all available evidence suggests that it does. Hawking also pointed to a piece of observational evidence that he found persuasive. If time travel to the past were possible, we should expect to see time travelers. The argument is simple. If any civilization anywhere in the universe ever develops backward time travel technology, they can visit any point in the past, including our present and our past. The fact that we do not observe visitors from the future is, at minimum, suggestive evidence that backward time travel is not possible. It is not conclusive, because the visitors might have reasons not to interact with us, or might be visiting in ways we cannot detect, or might be constrained by some self-consistency requirement that prevents paradoxes. But the absence of visitors is at least consistent with prohibition. What Hawking could not see from his position in 1992 was the mechanism. He suspected that quantum mechanics was involved, that the answer lay in the behavior of quantum fields near the putative time machine, that the instability he occasionally glimpsed in calculations was the hint of something systematic. But the calculation was extremely difficult, requiring the intersection of quantum field theory in curved spacetime with the specific geometry of closed time-like curves, and the tools for doing it cleanly did not yet fully exist. The mechanism, when it was worked out, turned out to be even more automatic and more elegant than Hawking had imagined, and the people who worked it out were, in large part, his own colleagues and students. The universe did not enforce causality through a rule, it enforced it through a feedback loop. And what that feedback loop implies about the nature of causality, about whether it is something imposed from outside or built into the very structure of reality, is the question that everything we're about to discuss is reaching toward. Part 6. The universe's defense mechanism. Imagine standing in a large hall, holding a microphone with a speaker at the far end of the room. When you speak into the microphone, your voice travels to the speaker, which amplifies it, which travels back to the microphone, which amplifies it again, which travels back to the speaker, and within a fraction of a second you have a screaming, painful feedback loop that started from nothing but your original words. Everyone who has set up sound equipment in a large room knows this problem. The solution is simple. Do not point the microphone at the speaker. Separate the input from the output spatially so that the output cannot feed back into the input. Now imagine that you cannot separate them. Imagine that the geometry of the room is such that no matter where you put the microphone and the speaker, sound always finds its way back from the speaker to the microphone. Imagine that the room is physically incapable of being arranged in a way that avoids feedback. In that case, you cannot use sound in that room at all. Every attempt to produce sound will immediately produce a feedback loop that destroys the sound equipment. This is, with appropriate translation into the language of quantum physics, essentially what happens to a traversable wormhole when it approaches the configuration required to become a time machine. In the early 1990s, Sung-Won Kim and Kip Thorne performed a calculation that has become one of the most important results in the physics of time travel. They examined what quantum vacuum fluctuations do inside a wormhole geometry as the wormhole approaches the critical configuration for producing closed time-like curves. Vacuum fluctuations are the quantum mechanical reality that the vacuum is not empty. The Heisenberg uncertainty principle guarantees that you cannot have a perfectly defined zero energy in a finite region of space for a finite period of time, so the vacuum constantly fluctuates, spontaneously generating and absorbing virtual particle-antiparticle pairs, briefly borrowing energy from nothing and paying it back before anyone notices. These fluctuations are not just mathematical abstractions, they produce measurable effects. The Casimir effect is one, the Lamb shift in atomic spectra is another. vacuum fluctuations are as real as anything in physics. Now, in the geometry of a wormhole, something unusual happens to these fluctuations. A virtual photon, one of the constantly generated quantum fluctuations, can enter one mouth of the wormhole and emerge from the other mouth. This is unremarkable in the ordinary case. But when the wormhole is close to the time machine configuration, when there is a significant time offset between the two mouths, the virtual photon emerges from the second mouth at a time before it entered the first mouth. It can then travel through ordinary space and meet itself entering the first mouth, and add its energy to the quantum state at the moment of its own creation, which then travels through the wormhole again and again and again. The vacuum fluctuation is the voice. The wormhole is the microphone speaker system. The geometry that causes the photon to arrive before it left is the reason the microphone is pointed at the speaker. And just like acoustic feedback, the energy of the fluctuation grows with each cycle through the loop. The Kip Thorne calculation showed that this growth is not slow. As the wormhole approaches the exact geometry required for a closed time-like curve to form, the energy density of the vacuum fluctuations in the wormhole throat diverges. It does not grow to some large but finite value. It grows without bound, approaching infinity as the critical configuration approaches. This divergence, this blow-up of the stress-energy tensor in the wormhole geometry, is what physicists call a quantum back-reaction. The quantum fields, reacting to the spacetime geometry, generate an energy density so extreme that it warps the spacetime geometry in return, and the warping destroys the wormhole before the closed time-like curve can form. This is automatic. It requires no intervention from outside. It requires no cosmic policeman checking the equations and deleting solutions that contain time travel. The physics does it by itself. The wormhole that tries to become a time machine generates, through quantum vacuum effects, exactly the energy density that prevents it from becoming a time machine. The would-be time machine is its own demolition crew. This is not a small result. It is one of the most remarkable self-referential loops in all of theoretical physics, and it is a loop that goes through both quantum mechanics and general relativity, which are the two frameworks that physicists have spent the entire 20th century trying and failing to reconcile. The chronology protection mechanism, at least in this version, requires both. It is quantum field theory protecting classical spacetime. It is the small scale governing the large scale in precisely the way that would prevent the larger scale paradox imaginable. Thorne himself was genuinely surprised by the result. He had spent years exploring the possibility of traversable wormholes, had found the energy requirements daunting but not formally prohibitive, and had hoped that some version of wormhole physics might survive as a theoretical possibility, if not a practical one. The Kip Thorne calculation suggested that the universe was considerably more aggressive in its defense of causality than he had expected. But here is what you should be sitting with right now, because this is the central pattern that everything else is going to reinforce. The mechanism that enforces causality protection here is not a rule. It is a consequence. It emerges automatically from the behavior of quantum fields in curved spacetime. Nobody wrote it into the equations. Nobody decided that causality should be protected and inserted a term to ensure it. The protection is a natural output of the physics, which raises the question, why? What is it about the deep structure of physics that produces causality protection as a natural output? Is the answer that causality is protected because it is built into the structure, not as a rule on top of the structure, but as the structure itself? We have now watched the universe refuse time travel twice, once with a price tag, once with a feedback loop. It will refuse again, and each refusal will point more clearly at the same answer. Part 7. Entanglement is geometry. In 2013, two physicists published a paper that looked, on its surface, like speculation. Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford proposed an equivalence that, if correct, would fundamentally change our understanding of what spacetime is made of. Their proposal was captured in a simple equation, written in the shorthand of physics notation, ER equals EPR. ER stands for Einstein-Rosen, the wormhole connection we discussed earlier. EPR stands for Einstein-Podolsky-Rosen, a famous 1935 paper by the same Einstein alongside Boris Podolsky and Nathan Rosen, which first described quantum entanglement and argued, incorrectly as it turned out, that entanglement was evidence quantum mechanics was incomplete. Quantum entanglement is the phenomenon where two particles can share a quantum state in such a way that measuring one particle instantaneously determines the state of the other, regardless of how far apart they are. This is not a signal. Information does not travel between them. The correlation exists in the shared state, and measuring it does not allow faster-than-light communication. But the correlation itself is real, non-local, and has no classical explanation. Two entangled particles separated by a universe share something that ordinary particles separated by any distance do not share. Maldacena and Susskind proposed that this sharing is not just a correlation, it is a geometric connection. Two maximally entangled particles, they argued, are connected by a microscopic Einstein-Rosen bridge. Not metaphorically, literally. The quantum entanglement and the geometric connection are the same thing described in two different languages. If you could see the fabric of spacetime at the quantum scale, entangled particles would appear as wormhole connections, tiny, microscopic, impossible to traverse, but real geometric features of spacetime. This proposal builds on work that Mark van Ramsdonk had published a few years earlier, in 2010, showing that entanglement between subsystems of a quantum theory corresponds to geometric connectivity in the spacetime that the quantum theory describes. Van Ramsdonk showed that if you imagine removing all entanglement from a quantum system that encodes a spacetime, the spacetime tears apart into disconnected pieces. Entanglement is literally what holds spacetime together. The implications are extraordinary. Spacetime is not a fixed background that quantum fields propagate through. Spacetime is built from quantum entanglement. The geometry we experience is an emergent property of quantum correlations between microscopic degrees of freedom at scales far smaller than any atom. The wormholes in ER equals EPR are not rare exotic objects that require extraordinary energy to create. They are the most common feature of spacetime. Every pair of entangled particles in the universe is connected by one, which means wormholes are everywhere, all the time, in the fabric of space itself. But they are none of them traversable. This is the critical connection back to the pattern we're tracking. The Einstein-Rosen bridges in ER equals EPR are microscopic, to the point of being meaningless for transportation. They are space-like in exactly the same way the original Einstein-Rosen bridge was space-like. Nothing can traverse them. They are connections in the topology of spacetime without being paths that matter, or information can follow. They are the bones of spacetime, but bones you cannot walk on, and they are causally harmless. Two particles connected by an ER equals EPR wormhole cannot use that connection to communicate. The connection exists, but it cannot carry signals. It cannot be used to create closed time-like curves. It cannot allow backward causation. The geometry is present in its most fundamental possible form, woven into the microscopic structure of spacetime, and even at that level, even at the level where spacetime is being constructed from quantum correlations, the causal structure is preserved. This is the pattern appearing at a new level of depth. If causality protection were just a feature of macroscopic wormholes, it might be an accident. But if causality protection is encoded into the microscopic quantum structure that spacetime itself is built from, then it is beginning to look like something more fundamental. It is beginning to look like causality is not a rule imposed on spacetime. It is a property that emerges necessarily from the quantum entanglement structure that produces spacetime in the first place. The protection is not outside. The protection is in the fabric. Part 8. Traversable wormholes that still don't break reality. For decades after the Morris-Thorne solution, the standard assumption in wormhole physics was straightforward, if daunting. Traversability required exotic matter. The only way to hold a wormhole open long enough for anything to pass through was to fill it with negative energy at scales that made the requirement feel less like a physics problem and more like a cosmic joke. The amount involved, roughly the rest mass energy of the entire Earth, arranged in a centimetre-thick shell of below vacuum energy density, was not just practically impossible. It was so far beyond anything naturally occurring or artificially producible that many physicists quietly filed traversable wormholes under mathematically interesting, physically irrelevant, and moved on to other problems. That assumption held for nearly 30 years, and then, in 2017, 3 physicists dismantled it. Ping Gao, Daniel Jaffrus, and Aaron Wall published a paper that changed the terms of the conversation in a way that the field had not seen since Morris and Thorne themselves. What they showed was that traversable wormholes could be created without classical exotic matter at all. Not with a reduced amount, not with a cleverly engineered substitute, without it entirely. The mechanism they found was quantum mechanical, arising not from any unusual material filling the wormhole throat, but from a particular kind of coupling between the two mouths of the wormhole itself. To understand what they did, it helps to think about what a wormhole mouth actually is in the mathematical description. Each mouth is a boundary, a surface where the ordinary spacetime on one side connects to the wormhole geometry. In the language of the quantum field theories that Gao, Jeffress and Wall were working with, each mouth can be thought of as a boundary of a quantum system, and quantum systems that share a boundary can be entangled with each other. They can be coupled. They can influence each other through quantum correlations in ways that have no classical analogue. What Gao, Jeffress and Wall found is that a specific type of quantum coupling between the two mouths, which they described using the technical language of double trace deformation, has a remarkable gravitational effect. When you entangle the two mouths of a wormhole in this particular way, negative energy flows into the wormhole throat not from any external exotic matter source, but from the quantum interaction itself. The entanglement between the boundaries generates the gravitational effect of negative energy in the interior. The wormhole, which would otherwise pinch off and become impassable, briefly opens, something can pass through, and then it closes again. The opening is transient, it does not last. But transient is not the same as fictional, and brief is not the same as impossible. Gao-Jeffress Wall is a genuine traversable wormhole in the theoretical physics literature in the fullest sense of that phrase. It requires no speculative exotic substances. It is consistent with quantum mechanics as we currently understand it. It produces real causal connectivity between two separated regions of spacetime. A signal enters one mouth and emerges from the other. That is traversal. That is real. And here is the part that should make you pause, because it is where the pattern we have been tracking through this entire journey shows up again, in a new model built from completely different tools. The Gao-Jeffress Wall wormhole still does not allow causality violation, not because someone added a rule preventing it, not because the researchers designed it that way, but because the mechanism that makes the wormhole traversable turns out to carry, embedded inside itself, the precise constraint that prevents backward time travel. The constraint works like this. Before the Gao-Jeffress Wall wormhole can be traversed, the two mouths must be coupled. That coupling must be established by sending a classical signal from one mouth to the other through ordinary spacetime, not through the wormhole, through regular space, at or below the speed of light the slow way. The classical signal has to arrive at the second mouth before the quantum coupling can be activated, and the coupling has to be activated before the wormhole can open, and the wormhole has to open before anything can pass through it. Follow the timing carefully, because this is where it gets precise. The activation signal leaves mouth A travelling at the speed of light. It arrives at mouth B after some time t, where t is the distance between the mouths divided by the speed of light. Only after t has elapsed can the coupling be activated. Only after the coupling is activated does the wormhole open. A signal then enters mouth A and emerges from mouth B. But the total elapsed time from the moment the activation signal left mouth A to the moment anything emerges from mouth B is always greater than t, always greater than the time light takes to cross the gap directly. What this means is that the Gao-Jeffress Wall wormhole never transfers information faster than light. You can use it. Something genuinely passes through it. But you could have sent the same information from mouth A to mouth B by ordinary light signal in less time, or at worst the same time, as doing it via the wormhole. The wormhole is not a shortcut in the causal sense. It is at best a tie with the speed of light, and you cannot create backward causation without beating the speed of light. So causality is preserved, not by design, by the internal structure of the mechanism that makes traversal possible in the first place. This is worth sitting with for a moment, because it is genuinely strange. The thing that opens the wormhole and the thing that prevents causality violation are not two separate features of the model. They are the same feature described from two different angles. The quantum coupling that generates traversability is the same quantum coupling whose timing constraint enforces causality. You cannot separate them. You cannot take the traversability and leave behind the causality protection. They come as a package, not because someone packaged them that way, but because the quantum information theory underlying the construction does not allow them to be separated. A year after Gao, Jeffress and Wall published their result, Juan Maldacena and Xiaoliang Qi extended the framework in a direction that made the physics even more concrete and even more striking. Where Gao, Jeffress, Wall had worked in the abstract mathematical setting of quantum field theories in curved spacetime, Maldacena and Qi showed that the same physics could be realized in coupled quantum mechanical systems, the kind of systems that exist in laboratories, the kind that quantum computers are built from. Their construction takes two quantum mechanical systems, couples them together in a specific way, and shows that the coupled system behaves exactly as a traversable wormhole would behave gravitationally. The description sometimes used for this, that quantum systems mimic gravitational behavior, is technically accurate but slightly misleading in its implications. It suggests that the quantum system is doing an impression of something gravitational, a performance rather than a reality. The more accurate framing is that gravity and quantum mechanics, at the appropriate scales and in the appropriate regimes, are the same phenomenon. The traversable wormhole in the Maldacena-Qi model is not a simulation of a wormhole. It is a wormhole, expressed in the language of quantum mechanics, rather than the language of curved spacetime, because those two languages are describing the same underlying reality, and the causality constraint is there too in exactly the same form. The Maldacena-Qi wormhole requires a prior classical coupling. The traversal cannot precede the coupling signal. Information does not travel backward in time. The constraint is not imported from the Gao-Jeffress-Wall result. It emerges independently from the quantum information structure of the Maldacena-Qi construction, which was built from different starting assumptions using different mathematical tools. Two completely independent methods of building a traversable wormhole. Two different mathematical frameworks. Two different physical descriptions. Two different research programs. The same structure, the same constraint. The same boundary drawn at exactly the line that preserves causality and no further. This is the point where coincidence stops being a reasonable explanation. When two independent experiments measure the same physical constant and get the same number, you conclude the constant is real. When two independent theoretical frameworks built from different foundations produce the same structural constraint, you conclude the constraint is real, not a feature of one model, not an artifact of one researcher's assumptions, something that the physics itself is insisting on, repeatedly, from every direction that physicists approach it from. What Gao, Jeffress, Wall and Maldacena-Qi together represent is not just two new wormhole models. They represent two more data points in a pattern that has now been accumulating for 4 decades, a pattern that is beginning to look less like a series of results and more like a single theorem that has not yet been written down in its final form. The theorem, if it exists, would say something like this. Every traversable wormhole, regardless of how it is constructed, regardless of what physical framework describes it, carries within its own construction the mechanism that prevents its use for backward time travel. The prohibition is not external. It is intrinsic. It is not added to the model. It is the model. And if that theorem is real, then the question it forces us to ask is not about wormholes at all. It is about causality, about what kind of thing causality actually is, and why the universe, in every framework we have ever built to describe it, appears to be made of it all the way down. Part 9. The We Built One moment. In late 2022, a team from Google announced something in the pages of Nature that produced one of the more heated scientific debates in recent memory. And when I say heated, I mean the kind of heated where physicists who are normally quite measured in their public statements started posting fairly pointed commentary on preprint servers within days of the paper dropping. The kind of heated where the gap between what the press release said and what the paper actually claimed became a minor controversy of its own. Science moves slowly and carefully most of the time, and then occasionally it produces a moment like this one, where a result lands in the middle of the field like a stone in a pond, and everyone scrambles to figure out how big the ripples actually are. The experiment used Google's Sycamore quantum processor, which at the time of the experiment was one of the most powerful quantum computing systems in the world. The team implemented what they described as a simulation of wormhole dynamics, specifically the dynamics associated with the Gao-Jeffress-Wall type traversable wormhole that we just finished discussing. The system they simulated was a highly simplified version of something called the sparse Sachdev-Yekitaev model, which is a particular quantum mechanical system that has been extensively studied because of its connections to quantum gravity and black hole physics. It is not a simple system to work with theoretically, but the version the Google team implemented used 9 qubits, which is, to be direct about it, an extremely small number for a system that is supposed to be capturing the physics of spacetime geometry. What they observed was a signal transfer between two sides of the system that the researchers described as being consistent with traversal through a wormhole rather than a round one. The distinction matters enormously, because in ordinary quantum teleportation, which is a well-understood process that quantum computers perform routinely, a quantum state can be transferred from one part of a system to another through classical communication and shared entanglement. This is real. It works. It has been demonstrated many times, and it does not require any reference to wormholes or spacetime geometry. What the Google team claimed was that their signal transfer showed a qualitative signature that distinguished it from ordinary quantum teleportation, a signature that they argued was evidence of genuine wormhole dynamics, rather than just entanglement doing its ordinary quantum mechanical thing. The claim landed on the physics community like a headline that is technically accurate and deeply misleading at the same time. Major news outlets ran stories with titles suggesting that Google had built a wormhole. This is not what happened, and the Google researchers themselves were careful in the paper to say it was not what happened. Though the gap between careful academic language and science journalism being what it is, the nuance did not always survive the translation. What the team had built was a quantum system that, according to their analysis, behaved in ways that are theoretically connected to wormhole physics. Whether that connection is deep enough to constitute a genuine realization of wormhole dynamics, or whether it is a more superficial correspondence that can be fully explained without any reference to spacetime geometry, is exactly what the debate is about. The criticism came quickly, and from credible sources. Several physicists argued that the signal transfer the Google team observed could be entirely explained by ordinary quantum teleportation without invoking wormhole dynamics at all, that the specific signatures the team pointed to as evidence of wormhole behavior were not actually unique to wormhole dynamics, and that a system of 9 qubits is so far from the limit in which the quantum system is expected to behave like a gravitational system that drawing conclusions about spacetime geometry from it is premature at best. The sparse Sachdev-Yekitaev model is theoretically connected to quantum gravity, but that connection becomes reliable only in a limit where the system is large, where the number of degrees of freedom is very large, and 9 qubits is not large in the relevant sense. It is, in the relevant sense, almost vanishingly small. Other physicists were more sympathetic. They acknowledged the limitations, but argued that the experiment was a meaningful proof of concept, a demonstration that the qualitative physics of wormhole dynamics could be studied on quantum hardware, even if the specific system was too small to make quantitative claims about quantum gravity. They pointed to the trajectory of quantum simulation as a field, where small systems studied today become the foundation for larger and more capable systems in the future, and argued that dismissing the experiment because of its scale was like dismissing the first transistor because it could not run a video game. The debate is genuinely unresolved. As of the most recent assessments in the theoretical physics literature, there is no consensus on whether the Google experiment demonstrated something specifically wormhole-like, or something that is fully explicable in purely quantum information terms without any gravitational interpretation. Both positions have serious physicists defending them. Both positions have serious physicists attacking them. This is, in its own way, a healthy sign for the field. Science is supposed to look like this when it is working at the frontier, messy and contested and unresolved, with people arguing carefully about what the evidence actually shows. But here is what I want you to notice, because it is the thing that connects this contested, debated, not fully resolved experiment back to the pattern we have been following throughout this entire journey. Amid all the disagreement about what the Google experiment demonstrated, there is one thing that nobody disputes. No violation of causality was observed, not even a hint of one, not a suggestion that the signal arrived before it was sent, not a whisper of backward time travel, not a single feature of the experimental results that would have surprised Stephen Hawking, or contradicted the chronology protection conjecture, or given anyone reason to believe that the causal structure of the experiment was anything other than completely conventional. Whatever the Sycamore experiment was or was not, it was causally well behaved. The signal went forward in time. Effects followed causes. The quantum processor did not accidentally become a time machine, while everyone was arguing about whether it had accidentally become a wormhole. The causal structure of the experiment was as ordinary as the causal structure of a light switch, despite the fact that the quantum dynamics being implemented were among the most exotic that any physical system has ever been asked to perform. This is, when you think about it, a remarkable thing to be able to say. The Google team was working at the absolute frontier of quantum hardware, implementing a system specifically designed to probe the boundary between quantum mechanics and quantum gravity, a boundary that we do not have a complete theory for, a boundary where our best theoretical tools start to strain and blur. They were doing physics that nobody has done before, in a regime that nobody has accessed experimentally before, and the result, for all its controversy and ambiguity and contested interpretation, was entirely consistent with causality. The most aggressive possible reading of the experiment, the reading in which the researchers genuinely did simulate traversable wormhole dynamics on a quantum processor, is still a reading in which nothing travelled backward in time. Traversable wormhole dynamics, whether in a theoretical model or in the closest thing to a physical realization that anyone has yet achieved, respect causality. They do not merely fail to violate it in dramatic ways. They appear to have causality compliance written into their structure at a level so fundamental that even a 9-qubit approximation of the relevant physics, running on hardware that did not exist a decade ago, in a regime where our theoretical understanding is incomplete, produces results that are causally impeccable. You can argue about what the experiment means for quantum gravity. You can argue about whether 9 qubits is enough to say anything meaningful about spacetime. You can argue about the difference between wormhole dynamics and quantum teleportation, and that argument is worth having. But you cannot argue that the experiment found a crack in causality, because it did not look for one and it did not find one, and based on everything else we have covered tonight, that is exactly what we should have expected. The pattern holds, even here, at the messiest and most contested edge of experimental quantum physics, even in a result that the field has not finished arguing about, the same boundary appears. Traversal, maybe. Backward time travel, no. A different mechanism producing the same refusal, in a completely different physical setting, using completely different tools, arriving at the same place that every other approach has arrived at for 40 years. At some point, a pattern this consistent stops being a pattern and starts being a law. We just have not written it down yet. Part 10. Wormholes without exotic matter. If the Gauss-Jeffreys wall result surprised physicists by showing that quantum effects could open a traversable wormhole without classical exotic matter, a result published in 2021 surprised them in a slightly different and perhaps even more fundamental way. Because this time, the surprise was not about finding a clever quantum mechanical workaround for the exotic matter problem. The surprise was about finding that the exotic matter problem might not be as central to the story as everyone had assumed, and that the universe might be considerably more comfortable with wormholes than 40 years of research had suggested. José Luis Blasquez Salcedo, Christian Knoll, and Eugen Radu were working in a framework that combined three things we know extremely well. Einstein's general relativity, which describes how mass and energy curve spacetime, the Dirac equation, which describes the behavior of fermions, the class of particles that includes electrons, quarks, and neutrinos, the particles with half-integer spin that make up all the ordinary matter in the universe, and Maxwell's equations, which describe electromagnetism, the force that holds atoms together and makes chemistry possible. There is nothing speculative in this list. These are not fringe theories or frontier conjectures. They are the most rigorously tested frameworks in the history of physics, equations that have been verified to extraordinary precision across decades of experiment. Blasquez Salcedo, Knoll, and Radu were not reaching for exotic physics. They were working with the most ordinary physics available, and in that combination of entirely ordinary physics they found wormholes, not approximately, not as a limiting case that required carefully tuned parameters to produce. They found a genuine class of wormhole solutions that are stable under perturbations, meaning they do not immediately collapse when you poke them, which is a non-trivial requirement that many proposed wormhole solutions fail. The solutions are consistent with everything we know about quantum fields and gravity, and they require no exotic matter in the classical sense, no hypothetical substance with negative mass or engineered negative energy density that you would need to imagine creating in a laboratory or mining from some speculative cosmic source. The mechanism that stabilizes these wormholes is the fermion field itself. Dirac fields, the quantum fields that describe fermions, have a specific behavior in curved spacetime that is different from the behavior of other fields. When you solve the Dirac equation in the curved geometry of a wormhole throat, the solutions have a character that produces, in effect, a negative energy density contribution to the stress-energy tensor that curves spacetime. This negative energy density is not coming from exotic matter. It is coming from the quantum mechanical properties of ordinary matter fields behaving the way they always behave, doing what the Dirac equation tells them to do, in a geometry that happens to be a wormhole throat rather than flat space, or a gravitational field around a star. The fermion fields that produce this effect are not special fermion fields that we need to synthesize or engineer. They are the fermion fields that exist everywhere in the universe already, as part of the quantum vacuum, as part of every atom of matter in existence. Electrons are fermions, quarks are fermions, every atom in your body contains fermions. The fields that stabilize BSKR wormholes are, in the most literal possible sense, made of the same stuff you are made of. This is the point where the result becomes philosophically significant in a way that goes beyond the technical details. For nearly 40 years, the standard framing of traversable wormhole physics was that wormholes required something the universe does not ordinarily provide. They required exotic matter, negative energy at scales and densities that nature does not produce spontaneously, that would need to be created through extraordinary means if it could be created at all. This framing placed wormholes firmly in the category of things that are mathematically allowed, but physically marginal, theoretically possible, but practically contingent on the existence of substances and conditions that might simply not exist anywhere in the observable universe. The BSKR result changes that framing. It says that wormholes are not contingent on exotic substances. They are contingent on ordinary matter behaving in the way ordinary matter always behaves, in a geometry that ordinary physics can in principle produce. The universe does not need to do anything special to contain wormholes. It needs only to contain what it already contains, which is to say, fermion fields and gravity, and it has both of those in extraordinary abundance. Wormholes, in the light of the BSKR result, are part of normal physics, not exotic physics, not frontier physics that might or might not connect to reality. Normal physics, the physics of electrons and quarks, and the electromagnetic force, combined with the physics of general relativity that governs how spacetime curves in response to energy and momentum. Now let us talk about the limitations, because they are significant and they matter for understanding what the result actually means. The wormhole throat sizes in the BSKR solutions are microscopic. When the researchers solved the equations and looked at what the geometry required, the throat sizes came out at scales ranging from the Planck length, which is roughly 10 to the minus 35 meters, and is the smallest scale at which our current description of spacetime is expected to remain valid, up to approximately the atomic scale at the most optimistic end. To put that in terms that give you a sense of the gap involved, a human hair is roughly 100 micrometers in diameter, which is 10 to the minus 4 meters. The atomic scale is roughly 10 to the minus 10 meters. The Planck length is 10 to the minus 35 meters. The difference between the Planck length and a human hair is 31 orders of magnitude. That is a 1 followed by 31 zeros. If you wanted to scale a Planck length wormhole up to human traversable size, you would need to increase its throat diameter by a factor comparable to the ratio of the observable universe to a single proton. This is not an engineering challenge. It is a statement that human-scale traversal of BSKR wormholes is not a realistic prospect in any framework that currently exists. A photon cannot pass through them. A neutrino cannot pass through them. Nothing macroscopic, nothing we could detect with any instrument we currently have or could reasonably imagine building, could traverse a BSKR wormhole. They are real in the mathematical sense, stable in the physical sense, and completely inaccessible in the practical sense. But here is the thing. Practical inaccessibility is not the point of the BSKR result, and evaluating it through the lens of whether it could be used for transportation misses what makes it important. The BSKR result matters because it tells us something about the character of the universe. Wormholes are not exotic intrusions into normal physics, rare and fragile configurations that require extraordinary conditions to exist. They are ordinary features of normal physics, emerging naturally from the same field equations that describe the matter and energy, present in every cubic centimetre of the universe. The universe is not a place that occasionally and reluctantly permits wormholes under very special circumstances. The universe is a place where wormholes are a natural consequence of combining gravity with the matter fields that fill it. There is a speculative but genuinely interesting observational possibility that some researchers have begun to discuss in connection with BSKR-type wormholes. Gravitational wave detectors, specifically LIGO in the United States and Virgo in Europe, have been detecting the ripples in spacetime produced by merging black holes and neutron stars since 2015, and the sensitivity of these instruments continues to improve with each observing run. If a population of microscopic BSKR wormholes existed in the spacetime surrounding a compact object like a neutron star or a black hole, they might produce subtle modifications to the gravitational wave signal that the object generates as it merges with a companion. The modifications would be small, potentially very small, and no such signature has been claimed in any existing gravitational wave observation. But the theoretical possibility exists, and it represents something that did not exist before BSKR, namely a potential observational window into wormhole physics using instruments that are actually operating and collecting data right now. This is speculative, but it is the kind of speculation that is connected to real measurements, and that is a qualitatively different kind of speculation from the purely theoretical kind. What the BSKR result adds to the larger pattern we have been building is something that operates at the level of overall picture rather than specific mechanism. We now have wormhole solutions distributed across an enormous range of physical assumptions, from the classical exotic matter requirements of Morris-Thorne at one extreme, through the quantum vacuum effects of the Kip Thorne back reaction calculations, through the entanglement-based microstructure of ER equals EPR, through the quantum coupling mechanisms of Gauss-Jafferis wall, through the quantum information framework of Maldacena-Key, and now to the ordinary Fermion field physics of BSKR. These solutions were developed by different people, in different decades, using different mathematical tools, starting from different physical assumptions, motivated by different questions. They span from the larger scales that general relativity describes to the smaller scales that quantum field theory addresses. They are about as different from each other as wormhole solutions can be, and every single one of them is causally harmless. None of them break causality. Not one, across the entire range of physical assumptions, across every framework physicists have brought to this question. The BSKR wormholes, the most physically grounded and least exotic wormholes ever written down, emerging from the most ordinary physics available, are still not going to let you visit the past. The most realistic wormholes we have ever found are still perfectly, impeccably, automatically consistent with causality. The universe does not need exotic matter to make wormholes. Apparently it does not need exotic matter to protect causality either. Whatever is enforcing that protection, it runs deeper than the matter content. It runs deeper than the specific model. It appears to run all the way down. Part 11. The pattern. Beneath the discoveries. Let us step back now, not to summarize what we have covered, because a summary would flatten something that deserves to be looked at whole. Let us instead do what physicists do when they have accumulated enough individual results to suspect that something larger is hiding behind them. Let us lay everything out on the table, side by side, and look at the shape of the collection, rather than the details of any single piece. We have 6 distinct classes of wormhole solution. They were developed over roughly 40 years. They were built by independent researchers working in different fields, using different mathematical tools, starting from different physical assumptions, motivated by different questions. Some of them did not know the others existed when they did their work. Some of them were not even trying to study wormholes specifically. The wormhole solutions emerged from their calculations as consequences of deeper questions they were asking about quantum gravity, or quantum information, or the behavior of fermion fields in curved spacetime, or the nature of quantum entanglement. The wormholes were not always the point. They showed up anyway. The first is the Einstein-Rosen bridge, published in 1935 by Albert Einstein and Nathan Rosen, while they were trying to understand the complete mathematical structure of the Schwarzschild solution to Einstein's field equations. This is the original wormhole, the one that started everything, discovered not by someone looking for a wormhole, but by the founders of relativity doing routine mathematical exploration of their own equations. The Einstein-Rosen bridge is structurally non-traversable. Nothing can pass through it. It exists for a geometric instant before collapsing, and even during that instant the path through it is space-like, meaning no physical object or signal can follow it. It does not produce closed time-like curves because nothing can use it. The causality protection here is not a mechanism. It is a structural feature of the geometry itself. The second is the Morris-Thorne wormhole of 1988, the first traversable wormhole solution in the history of physics, designed explicitly to allow a human being to pass from one region of spacetime to another through a geometric shortcut. This one requires negative energy at scales that are, to put it plainly, absurd. The rest mass energy of the entire Earth, in negative form, compressed into a centimetre-thick shell. When you push the Morris-Thorne wormhole toward the configuration required to produce closed time-like curves, quantum back reaction intervenes. The vacuum fluctuations of quantum fields, cycling through the wormhole loop, accumulate energy that diverges toward infinity at the critical threshold, and the resulting stress energy destroys the wormhole throat before the time machine configuration is reached. The causality protection here is a dynamic mechanism, automatic and self-executing, requiring no external enforcement. The wormhole dismantles itself. The third is the ER equals EPR structure proposed by Maldacena and Susskind in 2013, which operates at the most fundamental scale that wormhole physics has ever been applied to, the scale at which spacetime itself is being assembled from quantum correlations. In this framework, every pair of maximally entangled particles in the universe is connected by a microscopic Einstein-Rosen bridge. Wormholes are not rare, they are the fabric. They are everywhere, woven into the quantum structure of spacetime at scales far below anything observable, and they are entirely non-traversable, not because of an energy requirement or a feedback mechanism, but because the same quantum entanglement structure that produces them also constrains them to be space-like connections that no physical signal can follow. The causality protection is not imposed on the wormholes from outside. It is built into the quantum information structure that makes the wormholes what they are. You cannot separate the wormhole from its causal harmlessness, because they are the same feature described from two angles. The fourth is the Gauss-Jeffreys wall wormhole of 2017, which achieved something that most physicists had considered practically impossible: a traversable wormhole without classical exotic matter. The mechanism is quantum coupling between the two mouths, a specific entanglement that generates negative energy in the throat through quantum effects rather than classical matter. The wormhole briefly opens, allows something to pass through, and closes, but it requires a prior classical signal to activate, a signal that must travel from one mouth to the other through ordinary spacetime at or below the speed of light. The traversal cannot be initiated faster than that signal travels. The effective information transfer is therefore never superluminal, never backward in time. The causality protection here is embedded in the activation mechanism. It is not a separate constraint added to the model, it is the model. The same coupling that opens the wormhole is the coupling whose timing requirement prevents causality violation. The fifth is the Maldacena-Key coupled quantum systems model of 2018, which took the physics of Gauss-Jeffreys wall and showed that it could be realized not just in abstract quantum field theories, in curved spacetime, but in actual coupled quantum mechanical systems, the kind that can in principle be built in a laboratory. This is a traversable wormhole expressed in the language of quantum mechanics rather than the language of curved spacetime, and it respects causality for essentially the same reasons as Gauss-Jeffreys wall, derived through essentially different methods. Two independent approaches to the same physics, landing on the same constraint, articulated in different mathematical languages that turn out to be saying the same thing. The sixth is the BSKR Fermion wormhole of 2021, built from the most ordinary physics available, combining Einstein's general relativity with the Dirac equation for fermions and Maxwell's equations for electromagnetism. No exotic matter, no speculative substances, no assumptions beyond the standard model. The fermion fields that stabilize the wormhole throat are the same fermion fields that make up every atom of ordinary matter in the universe. The resulting wormholes are stable, consistent with known physics, and microscopic to the point of being entirely inaccessible for any practical purpose. They are causally harmless not because of a dynamic mechanism or a timing constraint, but because of their size. Nothing macroscopic can traverse them. They are the most physically realistic wormholes ever described, and they are perfectly, automatically, structurally consistent with causality. Now look at what these 6 have in common. And I want you to look carefully, because this is the thing that the individual results do not show you, the thing that only becomes visible when you look at the collection as a whole. They were developed independently, completely independently. The Einstein-Rosen bridge predates quantum field theory and curved spacetime by decades. Morris-Thorne were doing classical general relativity, not quantum information theory. Maldacena and Susskind were doing string theory and quantum gravity, not wormhole physics specifically. Gao, Jaffrus and Wall were doing quantum information and holographic duality. Blasquez-Salcedo, Knoll and Radu were doing classical field theory with quantum corrections. None of these groups was working in the same framework. None of them set out to prove that wormholes cannot violate causality. None of them was building on the other's causality results. They were each doing their own work, in their own framework, for their own reasons. And every single one of them found the same boundary. Traversal is allowed. Backward time travel is not. The permission and the prohibition land at exactly the line that preserves causality. Every time, without exception. Across frameworks that share almost nothing except the underlying physical reality they are all trying to describe. In physics, when you get the same result from independent approaches, the interpretation is clear. You're looking at something real. One derivation proves a mathematical result. 2 independent derivations suggest the result is robust. 6 independent derivations, using different mathematical structures, different physical assumptions, different conceptual frameworks, all converging on the same boundary, is not evidence of a result. It is evidence of a law. Even if you have not yet found the clean unified proof, even if the theorem has not yet been written down in its final form, the convergence itself is the signal. Physicists have a name for this kind of pattern. They call it convergent constraints. Each independent framework, when pushed toward the same question, generates a constraint that lands in the same place. This is structurally identical to how conservation laws emerge in physics. Energy conservation is not a rule that someone decided to impose on physical systems and then enforced from outside. It is a consequence of the time translation symmetry of the laws of physics, which was proved rigorously by the mathematician Emmy Noether in 1915. The conservation law is forced by something deeper, a symmetry property that every physical framework inherits, and it appears in every framework because every framework has to respect that symmetry, or it is not a correct description of physical reality. The convergence we see in wormhole physics is pointing at something analogous. Causality preservation may not be a rule written into physics from the outside. It may be a consequence of something deeper, some symmetry or structural feature of reality that every physical framework inherits automatically, the way every framework inherits energy conservation, and that therefore forces every framework to protect causality regardless of what other differences the frameworks have. The frameworks are different. The output is the same. The only explanation that fits this pattern is that the output is forced by something the frameworks share at a level more fundamental than the differences between them. What is that deeper thing? This is where we leave the territory of established results and step into the territory of genuine open questions, which is where the most interesting physics always lives. But the candidates are not vague. They are specific and they are testable in principle, even where they have not yet been tested in practice. One candidate is unitarity. Unitarity is the quantum mechanical requirement that the total probability of all possible outcomes of any physical process always sums to exactly 1. Information is never created from nothing and never destroyed into nothing. The quantum state of a system evolves in a way that preserves the total amount of information in the universe. Unitarity is one of the deepest constraints in quantum mechanics, so deep that violations of it are considered not just wrong, but incoherent, not a different kind of physics, but the absence of physics. And violations of causality, closed time-like curves and backward time travel, would in general also produce violations of unitarity, situations where information appears from nowhere or disappears into nowhere through the mechanism of the temporal loop. If unitarity is truly fundamental, then causality protection follows from it as a consequence, not as a separate rule, but as an output of the same requirement that makes quantum mechanics self-consistent. The second candidate is deeper and stranger, and has been gaining considerably more traction in the theoretical physics community over the last decade. It comes from ER equals EPR and the broader program of understanding spacetime as an emergent phenomenon. If spacetime is not fundamental, if it is constructed from quantum entanglement, the way a hologram is constructed from information encoded on a surface, then the causal structure of spacetime is not a property of spacetime that needs to be enforced. It is a consequence of the quantum entanglement structure that produces spacetime. The causal order of events is not imposed on spacetime from outside. It emerges from the same quantum correlations that generate spacetime itself. And quantum mechanics, which governs those correlations, does not permit them to be arranged in a way that produces backward causation, not because backward causation is forbidden, but because the quantum information structure that would be required to produce it is not a structure that quantum mechanics allows. In this picture, causality is not a rule in the universe. It is a property that the universe has because of what it is made of, the same way a steel beam has rigidity, not because rigidity is a rule imposed on steel, but because rigidity is what you get when you arrange iron atoms in that particular crystalline structure. Remove the structure, and you do not get a less rigid beam. You get no beam. Remove the quantum entanglement structure that produces causal spacetime, and you do not get a spacetime with different causal rules. You get no spacetime. This is the possibility that is quietly becoming the consensus direction in quantum gravity research, though consensus is a strong word for a field that does not yet have a complete theory. The emergence of time, the emergence of causal structure, the emergence of the arrow of time from quantum information theoretic foundations, these are active research programs with real results and real momentum, and every one of them points toward the same conclusion that our 6 wormhole solutions are independently pointing toward. If causality is the structure the universe is built from, not a constraint placed on top of the structure, but the structure itself, then the universe is not protecting causality the way a government protects a law, by enforcement and consequence. The universe is expressing causality the way a crystal expresses its lattice structure, because that is what it is, because the alternative is not a different version of the thing, but the absence of the thing entirely. Every wormhole that closes, every feedback loop that fires, every quantum coupling that insists on a prior classical signal, every microscopic throat that refuses to expand. These are not refusals, they are expressions. The universe is not saying no to time travel. The universe is showing you what it is made of, one failed time machine at a time. Part 12. What is the universe protecting? We have travelled a long way. We started with a phone call in 1985 and a novelist who wanted his heroine to travel to a star. That phone call became a paper. That paper became a research program. That research program ran for 40 years across 6 independent frameworks, built by researchers who were not coordinating their results, not working in the same field, not even always asking the same question. And every single one of them, without exception, found the same boundary. We have followed that boundary from classical geometry through quantum fields, through quantum information, through condensed matter physics, and back out the other side. And now we are standing at the place the entire journey was always pointing toward. The question we have arrived at is not technical. It is not about whether the energy requirements can be reduced, or whether some exotic matter state might someday be synthesized in a laboratory, or whether the gauge-Afras wall coupling could be scaled up from the microscopic to the macroscopic. Those are engineering questions, interesting ones, worth pursuing, but not the deepest thing here. The deepest question is simpler and stranger than any of those. It is this: what is causality? Not what does it do, not how do we use it, not what happens when it is violated. What is it? Where does it come from? And why does the universe, in every framework we have ever built to describe it, appear to be made of it all the way down? There are 2 broad answers to that question, and they lead to pictures of reality that are so different from each other that choosing between them is not just a physics problem. It is a philosophical problem about the nature of existence itself. The first answer is that causality is a fundamental law, a rule written into the universe at the deepest level, something that exists in addition to and alongside the equations of physics, a meta-rule that sits above the equations and says, no solution that violates causality is physically realized, regardless of what the equations would otherwise permit. In this picture, causality is like a cosmic speed limit, enforced by something that does not appear in any equation but whose existence is evidenced by the consistent fact that nothing goes faster than light and nothing travels backward in time. The universe runs on physics, and physics has this extra constraint sitting outside it, governing which solutions count as real. This picture has a certain intuitive appeal. It matches the way we often think about laws in general, as rules imposed on a system from outside, the way traffic laws are imposed on drivers by an authority external to the drivers themselves. And it has the virtue of being clear. Causality is protected because it is a law. Laws are enforced. The enforcement is what we have been observing in 6 independent frameworks over 4 decades. But this picture is philosophically deeply uncomfortable, and the discomfort is not aesthetic. It is structural. Physics is supposed to be self-contained. The laws of physics are supposed to determine what happens, completely and without remainder. If causality is a separate constraint imposed from outside the equations, then we do not have a complete theory of physics. We have a theory plus a rule that the theory cannot explain, and we do not know where the rule comes from or what enforces it, or whether there are other such rules we have not yet discovered. We have a physics with a ghost in it, a constraint that operates without a mechanism, an outcome without a cause, which is, when you think about it, precisely the kind of thing that causality itself is supposed to prevent. The second answer is different in kind, not just in degree. In this answer, causality is not a law at all. It is a property of reality that is so fundamental that reality cannot be assembled without it. Not cannot be assembled and still obey causality. Cannot be assembled, full stop. In this picture, causality is not the traffic officer standing at the intersection enforcing the speed limit. Causality is the road. Without the road, there is no intersection, no traffic, no officer, no speed. There is nothing. This picture is harder to hold in your mind because it requires you to think about causality not as a feature of the universe, but as a prerequisite for the universe. Not something the universe has, something the universe is. And the difference between those two things is the difference between a rule and a structure, between a constraint imposed on reality and the fabric from which reality is woven. The connection to ER equals EPR is direct and important here. If spacetime is built from quantum entanglement, if the geometry of space and the flow of time are emergent properties of quantum correlations between microscopic degrees of freedom at scales far below anything we can directly observe, then the causal structure of spacetime is not a property of spacetime that needs to be separately enforced. It is a consequence of the quantum information structure that produces spacetime. The causal order of events, the fact that causes come before effects, that the past is fixed and the future is open, that information flows in one direction and not the other, all of this emerges from the same quantum mechanical process that generates the geometry of spacetime in the first place. Remove the causal structure from the quantum entanglement that builds spacetime, and you do not get a spacetime with different causal rules. You get no spacetime. The entanglement that builds spacetime is structured in a specific way, a way that quantum mechanics constrains and governs, and that specific structure is what produces causal order. Change the structure so that causal order disappears, and the entanglement no longer produces spacetime. It produces nothing that physics can describe. Think about what this means in concrete terms, because the abstraction can make it feel more remote than it actually is. Every time a wormhole in our survey tried to become a time machine, the mechanism that prevented it was not an external intervention. It was an internal response of the system's own physics, operating through the system's own rules, producing the protection as a natural output rather than an imposed constraint. The quantum back reaction in the Kip Thorne calculation is not something extra that someone added to prevent time travel. It is the quantum field doing what quantum fields always do, obeying its own equations of motion in curved spacetime, and those equations in that geometry automatically generate vacuum fluctuations that cycle through the wormhole loop and accumulate energy that diverges at the critical threshold. The protection emerges from the physics. The constraint in Gauss-Jaffer's wall is not a separate rule appended to the model. It follows directly from the quantum information theory of the coupling, from the same mathematics that makes the traversal possible in the first place. The microscopic scale of BSKR wormholes is not a design choice made to ensure causal safety. It is the natural output of the Fermion field equations combined with gravity. The size the solutions come out at when you solve the equations honestly, without tuning parameters toward a desired result. The system is enforcing causality on itself from the inside using only its own rules. There is no external guardian standing watch. The guardian is the physics. The protection is not added to the physics. It is what the physics produces when you run it correctly. This self-referential quality, the way the physics generates causality protection as a natural output rather than having it imposed as an external requirement, is one of the most striking features of the pattern we have been tracking. It suggests that causality is not a boundary condition placed on the solutions to the equations. It is a property of the equations themselves, present in their structure, expressed in their solutions, unavoidable in any framework that correctly describes physical reality. Physicists working on the foundations of quantum gravity have been converging on a picture of reality that makes this even more explicit. In this picture, time itself is emergent, not fundamental, not a given. Not the stage on which events occur, but a property that appears when quantum systems of sufficient complexity interact in ways that generate thermodynamic irreversibility. The second law of thermodynamics, and the sense of before and after that we experience as the most immediate and undeniable feature of existence. The arrow of time in this picture is not written into the laws of physics as a fundamental asymmetry. It emerges from the quantum information structure of complex interacting systems, from the fact that information spreads and becomes entangled across many degrees of freedom in a way that is practically irreversible, even though the underlying quantum dynamics are time-symmetric. In this framework, the past is fixed not because a law says the past cannot be changed, but because the quantum information that produced the present is already spread across so many entangled degrees of freedom that reversing it is not forbidden. It is simply not a physically realizable operation at any scale that matters. The future is open not because causality grants permission for multiple possible futures, but because the quantum information that will produce the future has not yet been realized. The openness of the future and the fixedness of the past are both consequences of the same quantum information structure, the same spreading and entanglement of information across the degrees of freedom of the universe. This framework goes by several names in the technical literature. Causal dynamical triangulations is one approach, which builds spacetime from elementary causal building blocks and shows that the large-scale structure of spacetime emerges from the statistical behavior of those building blocks when causality is imposed as a fundamental ingredient. Loop quantum gravity is another, which quantizes spacetime itself and finds that the quantum geometry has causal structure built into its fundamental elements. The holographic principle with its associated information theoretic interpretation is a third, in which the physics of a volume of spacetime is encoded on its boundary surface, and the causal structure of the bulk physics is a consequence of the information theoretic properties of the boundary encoding. These are different approaches, they use different mathematics, they make different predictions in the regimes where they differ, but they share, as a common feature running through all of them, the emergence of causal structure from quantum information structure, the appearance of before and after as a consequence of how quantum systems encode and process information, rather than as a fundamental input to the physics. None of these frameworks is complete. Nobody has a complete theory of quantum gravity. That is the honest answer, and it is worth saying clearly rather than papering over it with confident language about what the final theory will look like. We are in the middle of the story, not at the end. But the direction all of these frameworks are pointing, the feature they share across their many differences, is exactly the causality protection that wormhole physics has been finding for 4 decades. The convergence is real, the pattern is real, the theorem, even if it has not yet been fully written down, is increasingly visible in the outline of its own shadow. The replica wormholes that appear in the modern resolution of the black hole information paradox are another thread in this picture, and they are worth mentioning because they connect our story to one of the longest-running problems in theoretical physics. When Stephen Hawking calculated in 1974 that black holes radiate thermally, he found something that seemed to imply that information was permanently destroyed when a black hole evaporated. Matter falls in carrying information about its quantum state. Thermal radiation comes out carrying no information about what fell in. When the black hole is gone, the information seems to be gone with it, which would violate unitarity, the most fundamental conservation law in quantum mechanics. The partial resolution of this paradox, developed over the last several years using a technique that involves summing over all possible geometries in a quantum gravitational path integral, requires including contributions from wormhole-like geometries that connect different copies of the spacetime in the calculation. These replica wormholes, as they are called, modify the calculation of the radiation entropy in a way that makes it follow the page curve, the behavior expected if information is preserved. The wormholes in this calculation are not traversable. They are not connecting different regions of a single spacetime in a way that anything physical could use. They are geometric configurations in a quantum gravitational sum that contribute to the correct answer, and their contribution is the thing that saves unitarity, that preserves information, that maintains the causal coherence of the physics. Wormholes, in this context, are not exotic intrusions into normal physics that create problems for causality. They are the thing that solves the problem. They are the geometric feature whose existence in the quantum gravitational path integral is what makes the physics consistent, what maintains the information preservation that unitarity requires, what keeps the causal structure of quantum mechanics intact. The wormholes that spend the rest of our story refusing to become time machines are, in this calculation, the heroes of the information paradox. Every thread leads back to the same place: information, causality, unitarity. The same cluster of properties, described in different languages depending on whether you're doing general relativity or quantum field theory, or quantum information theory, or thermodynamics, or wormhole physics. The cluster is always the same. The language changes. The underlying thing being described does not. This convergence is the most important thing our 40-year survey of wormhole physics has produced. Not any individual result, not the Morris-Thorne solution, or the Gauss-Jafrus wall construction, or the BSKR fermion wormholes, the convergence itself, the pattern. The fact that 6 independent frameworks, built by independent people, using independent mathematics, all find the same boundary, all protect the same property, all refuse the same outcome. That convergence is pointing at something that we do not yet have a name for, a principle that underlies all of the frameworks simultaneously, that forces them all to agree on this one thing despite agreeing on very little else. What that principle is, stated cleanly and completely, is the open question at the frontier of theoretical physics. We have its fingerprints. We have seen its effects in 6 different places. We know its output even if we do not yet know its face. And the output it keeps producing in every context, in every framework, at every scale is this: causality is preserved, not enforced, preserved. The way a crystal preserves its lattice structure not because a rule requires it to, but because the crystal is its lattice structure, and without the structure there is no crystal. We began this journey asking whether the universe enforces causality, or whether it is made of causality. We have now seen enough to say that the second answer fits the evidence better than the first. Not perfectly, not with certainty, but better. The universe does not appear to enforce causality the way a government enforces a law, with external mechanisms and consequences for violations. The universe appears to express causality the way matter expresses its properties, from the inside, as a natural output of what it fundamentally is. Every wormhole that collapses at the critical moment is not a refusal. It is a demonstration. Every feedback loop that fires as a would-be time machine approaches completion is not a veto. It is a revelation. Every quantum coupling that insists on a prior classical signal, every microscopic throat that will not expand to human scale, every entanglement structure that produces space-time connectivity without causal connectivity, is the universe showing you, in the only language available to it, the language of mathematics and physical law, what it is made of. We live inside that structure. We are assembled from it. The experience of time that you're having right now, the sense of this moment flowing into the next, of the past being real and fixed, and the future being genuinely uncertain, of causes preceding their effects in a way that makes action meaningful and memory possible, that experience is not a story you tell yourself about the universe. It is the direct, immediate, unavoidable experience of the most fundamental feature of physical reality. You do not observe causality. You are causality, organized into a form complex enough to wonder about itself. The door in Einstein's equations is real. It will always be real. Physics has mapped it from 6 different directions now, and every map agrees. The door exists. The geometry permits it. The mathematics allows it. And the mechanism by which the universe declines to let it open is not a lock placed on the door by some external authority. The mechanism is the door itself. The structure that makes the door possible is the same structure that makes opening it impossible. You cannot separate them. The door and its closure are one thing. What is the universe protecting? Sit with that question for a moment, because the answer the physics is pointing toward is strange enough to deserve a moment of genuine stillness. Perhaps the universe is not protecting anything. Perhaps protection is the wrong frame entirely, a frame that assumes an external agent doing the protecting, a guardian outside the system keeping something safe from something else. Perhaps what looks like protection from the outside, from the perspective of a physicist trying to build a time machine and watching it fail, looks like something completely different from the inside, from the perspective of the physics itself. From the inside, there is no protection. There is only structure. The structure that makes events possible. The structure that makes before and after meaningful. The structure that makes it possible for there to be a here and a now and a you experiencing both. That structure is causality, and the universe is not protecting it any more than a river protects water. The river is water, organized by gravity and terrain into a particular flowing form. The universe is causality, organized by quantum information and spacetime geometry into the particular structured form we call physical reality. We are not trapped inside causality. We are causality, temporarily organized into beings capable of asking whether there is anything outside it. The wormholes that keep closing are not doors being slammed in our faces. They are mirrors, every one of them, reflecting back at us the structure of the thing we are standing inside of, showing us its shape in the only way a structure can show you its shape, by showing you where it ends. That is where physics stands tonight. Not at a conclusion, at a threshold. The question has been running for 40 years, and it is sharper now than it has ever been. What is causality? What is time? What is the universe made of at the level below which there is nothing left to go below? We do not know yet. But we have something better than an answer. We have a pattern so clear that the answer, when it comes, will not surprise us. We will recognize it. We have been circling it for 4 decades, approaching it from 6 different directions, watching it hold firm against every attempt to find an exception. When someone finally writes down the theorem that unifies all 6 frameworks and proves what the pattern has been showing us all along, it will feel less like a discovery and more like finally seeing clearly something that was always there. The physicists who spent 40 years trying to walk through that door were not failing. They were doing what physicists do best. They were mapping the boundary of the possible so precisely that the shape of the impossible became, in its own way, the most informative thing in the room. Every closed time-like curve that never formed was data. Every wormhole that self-destructed at the critical moment was evidence. Every quantum coupling that refused to go faster than light was a measurement of something real. We are causality observing itself, through instruments made of mathematics and curiosity, finding at the bottom of every question the same answer wearing a different face. The universe is not keeping us out. It is showing us, in the only language it has, what it means to be in.